My name is Victoria Crawford, and I'm presenting my paper, Scalable Bicriteria Algorithms for Non-Monotone Submodular Cover. So in this paper, I'm going to present some algorithms for a certain class of optimization problems. So our setting is that we have some universe U, which is of finite size, and we're going to be looking at set functions over this universe U that have this property called submodularity. So intuitively, a submodular set function, so this is a diminishing returns property. So if we have a set A, a subset of B of the universe, and then X is not in B, then the marginal gain to F of adding X to A is at least as high as the marginal gain to F of adding X to B. So some applications where the submodular set functions arise is if U is some data set, and we're looking to find a subset of the data set that effectively summarizes it, then we can define some measures of summary quality that have the submodular set function property. Another application is in cutting in a graph. So in this application, the universe U would be vertices. So if we define F to be, if you take a subset of the vertices, the number of edges between that set of vertices and its complement, then that function is also submodular. So specifically in this paper, I'm considering the submodular cover problem. So we have our submodular set function F. We also have a cost function C defined on elements of the universe that gives each element some cost. And then a threshold tau, which is some value that you want your function F to be above. So submodular cover, we want to find the minimum cost subset of the universe such that the F value of this set is at least tau. So if we look at data summarization, again, how submodular cover would arise is if we were formulating an optimization problem describing how we want to condense this set U down into the smallest memory set possible, but it gets F above some threshold, so that would correspond to summarizing the entire data set sufficiently well. And in graph cut, submodular set cover would mean we want to take the smallest set of vertices whose removal would disrupt sufficiently many edges. So in addition to submodularity, a lot of the time papers assume that the function F is monotone. So this means that for A subset of B, F of A is less than or equal to F of B. But in this paper, we're not assuming that F is necessarily monotone, only that it's submodular. So another thing to think about is that a lot of these applications of submodular cover involve really large data sets. So when we develop algorithms for it, we need to think about whether these algorithms are able to scale to the really large data sets. So the contributions of this paper is, first of all, this formulation of submodular cover is novel, since this paper is the first to consider submodular cover where F is not assumed to be monotone, only submodular. And so for this new problem, this paper develops several bicriteria approximation algorithms that are scalable to large data sets. There's also included an experimental evaluation on max cut and data summarization applications. So first of all, for this problem, we're going to present some alpha beta bicriteria approximation algorithm. So let opt be the cost of the optimal solution for an instance of submodular cover. Then an alpha approximation algorithm would return a feasible solution A such that cost of A is at most alpha times opt. An alpha beta bicriteria approximation algorithm doesn't necessarily return a feasible solution. It returns a solution A such that the cost of A is at most alpha times opt and F of A is at least beta times tau. So the way that the algorithms proposed in this paper are scalable. Typically the time is measured in queries of F. So these algorithms have relatively low numbers of queries to F. In addition, the algorithms are somewhat in a streaming setting where it's assumed that the algorithm has limited memory for elements that it's going to store and that it's going to these algorithms work by basically processing U, the ground set, in a stream in arbitrary order, and they make either one pass or very few passes through the data set. So at the core of the several algorithms proposed in this paper is this subroutine called stream. So stream is essentially like a filtering down procedure. It goes through the universe U in one pass in an arbitrary order and picks a much smaller set compared to U. So as an input, the algorithm stream requires a guess of opt, the cost of the optimal solution, and it uses that guess in order to decide what elements of the universe to discard or to keep. So basically, it has these 2 over epsilon disjoint sets, S1 through S2 over epsilon, and the total size of these sets is proportionate to the guess of opt. So basically, if you have a small guess of opt, you know that the size of all of these sets that you're storing is relatively small. So in addition, so once we make this pass through the data set, filtering down to these 2 over epsilon disjoint sets, this stream algorithm then runs an algorithm for unconstrained submodular maximization on the union of these sets. So unconstrained submodular maximization is the optimization problem where we simply want to maximize F over all subsets of the universe. And then once it runs that algorithm, it returns the output of that algorithm. So the first algorithm for submodular cover presented in the paper is multi, and so it uses stream as a subroutine. So it's called multi because it makes multiple passes through the data set U. Each pass corresponds to a run of stream. So stream requires an input that's a guess of the optimal solution. So basically, multi is making increasingly large guesses of opts, running stream through the data set, looking at what sort of solution stream returns, and if it's good enough, then it finishes. If it's not good enough, then it makes another pass with an increasing guess of opt. So it's basically picking bigger and bigger sets. So it's proven in the paper that once it gets a sufficiently good guess of opt, then it's going to exit. So the theoretical guarantees in the paper, so you can see the particular details as a theorem statement in the paper, but multi is proven to be a bicriteria approximation algorithm. So this gamma term here is the approximation guarantee of the unconstrained submodular maximization algorithm. So at best, that's going to be 1/2. And actually, in the paper, I prove that you can't really do better than that in terms of approximating the feasibility constraint. Also, it's proven that multi takes few passes through U, that it has low total stored cost relative to the opt, the cost of the optimal solution, and also has relatively low queries of F overall. So in addition to multi, there's an algorithm called single presented in the paper. It has a similar idea to multi, but instead of sequentially making guesses of opt, it makes them in parallel. So the benefit of single is that it only goes through the universe U in one pass, but the problem is that it doesn't really have a true bound on its memory the way that multi does. Instead, it has more of like a competitive bound. It also runs the unconstrained submodular maximization algorithm a lot more than multi does, so it can have a lot more queries to F compared to multi. So the benefit of single is really if you wanted to take a single pass of your data, and that would just depend on your application. So experimentally, I also looked at different unconstrained algorithms that we're using as a subroutine for stream. So basically, single, I said it runs unconstrained submodular maximization a lot of different times. So in order to reduce the query complexity, I used a very fast algorithm for that unconstrained submodular maximization. So actually just returning a random set. On the other hand, in the experiments, when I'm running the multi, which uses less runs of the unconstrained submodular maximization algorithm, I just used the algorithm for it that gives the best approximation guarantee, which is 1/2. So, so in these experiments, I looked at the different algorithms for different input. So epsilon is an input parameter, and it controls your trade-off between your approximation guarantees and the feasibility and on the cost. So I looked at the F values of the return solutions, C, the cost, the total number of queries, and the maximum memory at any point the algorithms used. So I found in terms of F, both algorithms performed multi and single very close to their theoretical guarantees, which actually makes sense. If you were to read the paper, it makes sense. And basically the differences in F and C between these two algorithms is primarily because of the different unconstrained algorithms being used. So in the paper, I run them with the same, and you can see that their F and C values are almost identical. But like I said, if you use a slower algorithm for the unconstrained subroutine for single, you have to make a lot more queries to act. So that's why in these experiments, I didn't continue to do that. So also in other experiments, I looked at different thresholds, and I also compared multi and single to an alternative way of solving non-monotone submodular cover, and that's by using submodular maximization algorithms, but they don't have as good of theoretical guarantees if you do that. But I compared them, and basically multi outperforms the other algorithms in all measures except for cost. So it tends to return solutions with higher cost compared to the other algorithms. And the main benefit of single is it's just really the only one that makes a single pass through the universe U. So thank you for listening to my talk. If you have any further questions, feel free to contact me at vcrawford@tamu.edu.